Welcome back to Iron Process, where we break down the most powerful and awe-inspiring industrial operations on the planet. Today, we step into a domain where steel is not just shaped, but reborn. A place where massive vessels are torn apart, rebuilt, and pushed back into the ocean with renewed life. Under the glare of welding arcs and the heat of molten metal, a world driven by pressure, precision, and raw engineering intensity unfolds. Let's begin. As dawn rises over Lisnave, one of the most critical hubs along the Atlantic Maritime Corridor, the scale of operations becomes immediately apparent. Spanning over 1.5 million square meters, this is far more than a conventional shipyard. It is a strategic lifeline, a place where vessels from around the world arrive for high-level maintenance, repair, and transformation before returning to global service. Inside the workshops, engineering precision takes center stage. Complex systems, from high-performance turbochargers to massive propeller assemblies, are carefully dismantled, restored, and recalibrated. Every surface is refined down to the smallest detail, ensuring optimal efficiency when the ship re-enters open water. Across the steel fabrication and piping zones, the environment is alive with energy, illuminated by continuous bursts of welding light cutting through the air. Structural reinforcement takes place on a massive scale. Entire sections of piping networks are replaced or upgraded, forming a dense and highly engineered internal system. Electrical components, the operational backbone of the vessel, undergo rigorous inspection procedures where every connection is verified to meet strict reliability standards before departure. Once internal power is fully restored, the vessel transitions into its external transformation phase. The entire hull is treated using specialized coating technologies, forming a resilient shield against the aggressive corrosive forces of saltwater environments. Alongside these processes runs an uncompromising system of quality control, supported by continuous workforce training programs that ensure all operations meet the highest benchmarks in safety and environmental compliance. At Lisnave, operations never stop. Running continuously around the clock, the shipyard functions as a non-stop industrial engine, bringing vessels back to life through day and night cycles. The guiding principle here is clear. Customer trust defines strength. This is not just a statement, it is a commitment embedded into every stage of the process, ensuring each vessel leaves fully prepared to continue its role in connecting global trade networks. Shifting to another critical operation, MEC Panama stands at the center of a highly technical engineering campaign. The cargo vessel MV Mariner undergoes a complex structural intervention focused on removing and replacing the aft peak bulkhead. The operation begins with controlled thermal cutting, designed to relieve internal structural stress while maintaining overall stability. Using gas torches generating temperatures in the thousands of degrees Celsius, sections of fatigued steel are precisely removed. This exposes the internal load-bearing framework, revealing the core structural integrity of the vessel. However, the true challenge lies not just in removal, but in reconstruction, particularly under high humidity conditions where weld quality must remain uncompromised. Integrating new hull plates into the existing structure is far beyond a simple repair. It is a full-scale reconstruction effort aimed at restoring complete load-bearing capacity. Each weld seam is subjected to ultrasonic testing, UT, ensuring absolute structural reliability under the extreme forces encountered during transoceanic operations. The successful execution of the MV Mariner project highlights MEC Panama's ability to minimize downtime while maximizing operational efficiency for ship owners. From the intense welding activity along the docks to the final layers of protective coating, every step reflects the strict demands of modern shipbuilding standards. Moving to Varna, Bulgaria, Odessa Shipyard, a facility with roots dating back to 1955, is undertaking one of its most demanding projects, the structural overhaul of the chemical tanker Stolt Asudo. As daylight intensifies, so does the pace of operations. Technical teams initiate surface preparation while applying primary coating layers across the vessel. At the same time, branding elements are refined. The Stolt tanker's Asudo identity is sharpened, and its signature yellow exterior is restored with precision. This stage is not just technical, it is symbolic. It marks the restoration of the vessel's corporate identity. From here, multiple work streams are executed in parallel. The main engine undergoes detailed inspection and repair to ensure maximum performance output. Meanwhile, the deck piping system, known for its complexity in chemical transport vessels, is fully dismantled, cleaned, and recalibrated. Heavy lifting systems are deployed to handle oversized components, ensuring that each movement, inspection, and reassembly step is executed with complete accuracy and safety. Yet, the most demanding operations remain below the waterline. Critical propulsion and steering systems, including the propeller, rudder stock, and bow thruster, must be serviced within extremely tight tolerances. Externally, the vessel undergoes a complete transformation. The aged hull surface is stripped entirely and replaced with a new coating system. A specialized anti-corrosive red layer protects submerged sections, while the upper structure is finished in its iconic yellow. Beyond aesthetics, this coating system serves as a critical defense against the harsh marine environment. In the final stage, focus shifts towards system commissioning and crew conditions. The accommodation areas are upgraded, creating a safer and more comfortable living environment for extended voyages. At the same time, engineers conduct final system checks, resolving any remaining issues and fine-tuning performance across all operational systems. A final finishing coat is applied, giving the vessel the appearance of a newly launched ship. With all work completed, the dry dock is gradually flooded, lifting the vessel back into the water. This moment marks the full completion of the overhaul process. Support tugboats guide the Stolthaven Basuto safely out of the yard. Fully operational once again, the vessel is ready to rejoin global shipping routes. It is a powerful visual, a machine reborn through engineering precision. Next, we move to Saint-Nazaire, where one of the largest cruise ships ever built, Harmony of the Seas, enters scheduled maintenance inside a massive dry dock. This moment is rare. The shipyard has opened access, revealing the immense scale of operations to the outside world. Standing at the base of the dry dock, the sheer size of the structure is overwhelming. The hull towers upward like a 20-story wall of steel. Stretching across 362 meters in length, the vessel dominates the entire space, a true monument of modern maritime engineering. Moving toward the stern, the focus shifts to one of the most advanced propulsion technologies ever deployed at sea, the Azipod system. Unlike traditional shaft-driven propellers, these electrically driven pods rotate a full 360 degrees, delivering exceptional maneuverability for a ship exceeding 220,000 gross tons. At the bow, multiple thruster systems are embedded within dedicated tunnels running through the hull, allowing precise lateral movement during docking operations with minimal reliance on tug assistance. Above, elevated work platforms continue to lift technicians into position, enabling detailed inspection of structural joints and forward-facing sensor systems. At the front of the vessel lies the bulbous bow, a carefully engineered protrusion that disrupts wave formation, reducing hydrodynamic resistance and improving fuel efficiency. Once inspections across the entire structure, from keel to superstructure, are completed, the dry dock will be flooded and the vessel will return to open water. In another major engineering operation, a large-scale military shipbuilding project unfolds under the expertise of BAE Systems. This is not conventional construction. Instead, the process relies on modular fabrication, where massive steel sections are built independently, pre-equipped with integrated mechanical and electrical systems before final assembly. This phase demands absolute control over mechanical risk. Self-propelled modular transporters, known as SPMTs, equipped with hundreds of independently controlled axles, are deployed to move sections weighing thousands of tons into position. bow, midsection, and stern are gradually aligned with extreme precision before being secured into a unified structure. Welding teams operate continuously, fusing these enormous steel blocks into a single watertight hull. While the main structure is assembled, the superstructure, including the bridge and command center, is fabricated separately and transported via barge. Heavy lift cranes then position these massive sections with surgical accuracy onto the main deck. The vessel reaches a symbolic milestone during its naming ceremony. Following maritime tradition, a bottle of champagne is broken against the bow. Moments later, the completed structure begins its controlled descent into the River Clyde, accompanied by thousands of spectators and a cascade of confetti. As the hull meets water, tugboats immediately move in to stabilize and guide the vessel. With the primary structure completed, the ship enters the outfitting phase. Within a floating dock, large bronze propellers are installed, along with the bow dome housing advanced sonar systems. The next stage involves erecting the main mast systems. At the highest point sits the Samson radar, a critical component functioning as both the detection and control center for the vessel's air defense capabilities. The warship then progresses into its armament phase. Advanced naval gun systems and close-in defense systems are installed and calibrated with precision by specialized teams. Once operational, the vessel departs for sea trials, a critical testing phase under real-world conditions. Despite its massive scale, the ship demonstrates high agility, executing tight maneuver patterns, including figure-8 turns in open water. Operational testing extends further. Special Forces units deploy high-speed, rigid hull inflatable boats directly from the vessel. Under severe weather conditions and heavy waves, the ship conducts live fire exercises, validating both stability and combat system performance. After successfully completing all test phases, the vessel returns for its commissioning ceremony. The Royal Navy ensign is raised. Crew members line the flight deck in full formation. What was once an inert assembly of steel is now a fully operational warship, ready to integrate into global maritime defense operations. Elsewhere at Baku Shipyard, another major construction project takes shape, the next-generation Ro-Pax ferry Azerbaijan. The assembly process advances rapidly. A 300-ton gantry crane lifts massive hull blocks into place, aligning each section with absolute precision. Gradually, the vessel's internal framework emerges, revealing a robust system of bulkheads and structural supports. This is the stage where the vessel's identity begins to form. The bow section is installed, followed by the full superstructure, including passenger cabins and the navigation bridge. Each layer of steel receives a protective anti-corrosion primer, preparing the vessel for final finishing stages. At the same time, attention shifts toward internal propulsion systems. Engineering teams install propeller shafts and large screw assemblies, the core mechanical components that will drive the vessel across vast ocean distances. With structural work nearing completion, the vessel transitions into the painting phase. The coating process is executed methodically, using 3 primary colors: white, blue, and red. The name Azerbaijan is inscribed onto the hull, marking the completion of its external identity. From here, focus moves toward interior outfitting and aesthetic finishing. The vessel adopts its full visual profile, defined by its signature color scheme. Inside, the environment contrasts sharply with the industrial exterior. Passenger areas are developed to hotel-grade standards, including fitness facilities, dining spaces, and a modern digital bridge equipped with advanced navigation systems. Before delivery, the vessel undergoes extensive operational testing at sea. Critical loading systems, including stern ramps, cargo hatch covers, and vehicle lifts, are repeatedly tested to ensure reliability. The cargo deck is engineered for maximum efficiency, accommodating both heavy freight vehicles and passenger transport within a highly optimized spatial design. In 2021, the Azerbaijan is officially launched. This project not only reinforces Baku Shipyard's regional leadership, but also represents a strategic advancement in national transport and energy infrastructure. It stands as a symbol of engineering progress and maritime capability. Meanwhile, in Amsterdam, another high-level engineering challenge unfolds aboard the Polarcus Nyla, one of the most advanced 3D seismic survey vessels in operation today. This operation goes far beyond routine maintenance. It is a full-scale propulsion modernization program, a highly complex engineering campaign designed to redefine the vessel's performance at sea. Even for a shipyard with more than 80 years of experience, the scale and technical demands of this project present a significant challenge. The team moves forward with determination, fully aware of both the opportunity and the risks involved. Under the pressure of an unforgiving deadline, every phase must be executed with maximum efficiency. Work intensity increases across all departments as crews push to maintain operational precision. The scope of the upgrade spans multiple critical systems, including propulsion reconstruction, installation of a new ballast water treatment system, and the integration of additional support vessels and davit systems. Time becomes the defining factor. Parallel operations unfold simultaneously. Nylon Steel takes responsibility for the prefabrication and installation of gondola structures. The removal of the existing 60-ton thrusters requires extreme accuracy and advanced technical coordination. This step is critical. Any delay or error directly impacts the entire project timeline. The next challenge is logistical. 2 gondola units, each weighing 100 tons, must be transported and installed under strict safety conditions. Roads are closed. Movement is carefully controlled. With support from Mammoet, a parallel lifting system is deployed, lowering each unit into position within the dry dock with precise control. Once in place, the gondolas are elevated and aligned with the hull. Teams operate continuously, ensuring all parameters meet exact engineering specifications. Following alignment, support structures are removed and welding operations begin. Every joint is inspected before the installation of the propellers proceeds. Rudder systems are prepared. Bolts are tightened to exact torque values. In the dry dock environment, time directly translates to cost, making efficiency a constant priority. Once all preparatory steps are complete, the new propellers are installed under strict supervision, with every detail verified to ensure precision and operational safety. This milestone reflects months of coordination and sustained effort from the entire workforce. With installation complete, the vessel undergoes cleaning using advanced surface treatment systems, followed by the application of eco-friendly anti-fouling coatings in accordance with Polarcus standards. The refreshed blue and white exterior gives the vessel a renewed identity, as if newly launched. On a mist-covered evening in April, the project reaches completion. The upgraded Polarcus Nela is now ready to return to service. The success of this operation demonstrates not only the technical capability of Damen ship repair, but also the strength of collaboration between engineering teams working under intense pressure. However, not all maritime operations are controlled, planned upgrades. When disaster strikes at sea, the industry shifts into an entirely different mode, salvage operations, where every second matters and environmental conditions dictate the limits of engineering. The incident began on January 17, 2013. The U.S. Navy minesweeper USS Guardian ran aground on Tubataha Reef in the Sulu Sea. Initial recovery attempts by nearby vessels failed to free the ship. With the hull severely compromised and the engine room flooded, a complete power failure followed. The decision was made to evacuate the entire crew to ensure safety. Under continuous pressure from currents and wind, the vessel was pushed further onto the reef, rotating 90 degrees and worsening the situation. Technical assessments revealed severe damage to the keel, propellers, and rudder, all embedded deeply into coral and seabed. Direct towing was no longer an option, as it risked destroying the fragile reef ecosystem. This operation became more than engineering. It became a conservation mission. Tubataha Reef is a UNESCO World Heritage Site, one of the most sensitive marine ecosystems on the planet. Strict conditions were imposed: zero oil leakage, zero falling debris, and absolutely no additional damage to the coral structure. The salvage operation began with fuel extraction and the removal of all loose equipment from the deck. Due to the steep underwater terrain, conventional crane vessels could not anchor safely. Instead, the salvage team deployed the Jascon 25, a dynamically positioned vessel capable of maintaining exact position without dropping anchor. This technology became critical to protecting the reef. The dismantling process began from the top. Sections of the superstructure, including cabins, antenna systems, and funnels, were cut away and lifted onto transport barges. Removing this weight reduced pressure on the reef and enabled the next phase. To fully extract the vessel, the hull itself had to be cut into 4 massive sections. Inside, heavy engine systems were removed to further reduce structural load. Every cut required absolute coordination between cutting crews and crane operators. Each lifted section had to be controlled precisely to avoid contact with the reef below. One by one, the bow, auxiliary engine section, main engine section, and stern were removed from the site. After each extraction, teams conducted strict monitoring to ensure no debris remained. The final phase focused on complete environmental cleanup. Divers collected even the smallest fragments using specialized equipment. On April 3, 2013, the reef was officially cleared. This marked the conclusion of a model salvage operation, one that successfully balanced engineering execution with environmental preservation. Looking across all these operations, from repair yards to new construction, modernization projects to high-risk salvage missions, a broader picture begins to emerge. The modern maritime industry is not a single system, but a vast global network. A system where engineering, technology, organization, and human effort converge into one continuous process. Every stage is interconnected. Every operation depends on precision. Standards continue to rise, requiring constant adaptation, learning, and innovation. Yet, despite all technological advancement, one factor remains unchanged: the human element. Machines may evolve, automation may expand, But in the end, it is the skill, experience, and discipline of engineers and workers that define success. They are the ones who transform raw steel into functional vessels, machines capable of crossing oceans, transporting goods, connecting economies, maintaining security, and expanding the boundaries of human activity. Each ship leaving dry dock represents more than an industrial product. It becomes part of a global system, carrying cargo, energy, people, and information across borders. With it comes the transfer of economic value, political influence, and social connection. Ensuring that these vessels operate safely, efficiently, and sustainably contributes directly to the stability of the global system. In the end, this narrative is not only about engineering processes, it carries a deeper meaning. The modern maritime industry stands at the intersection of advanced technology, global coordination, and long-term responsibility. It is a domain where humanity continues to push beyond limits of materials, of environment, and of its own capabilities. Every ship that leaves port begins more than a physical journey. It carries a mission to connect the world, a mission that never ends. Thank you for staying until the end. If you value content like this, make sure to like, share, and subscribe so you don't miss what comes next. Iron Process signing off. See you in the next one.